Hello and welcome everybody. Today we're going to talk about Bezout's Lemma. First things first, my apologies for any mispronunciation. On the internet it says Bezout. Um, I've also heard Bezout. It's French and I'm not a French dude. Um, yeah, I'll just say call it Bezout. Okay, Bezout's Lemma. This is quite a difficult one. It's quite long. Um, the at the end of the proof, it's simple, but there's a huge proof, and yeah, let's get started. Um, before they're like basically four steps, but let me get the basics out first. Let a and b, which belong to the set of integers, uh, and the thing is not they're not both zero. So it's possible that a could be zero and not b, or b could be zero not a, but not both zero. Um, then then there exists x and y belonging to the set of integers such that GCD of a comma b equals ax plus by. And if you remember, I'm gonna put this the video over here somewhere. I'm still new to doing that, but yeah, I'm gonna put the link over here. This is kind of like the GCD characterization theorem, where d equals ax plus b. Then we proved that d is actually the GCD, but now we're gonna prove that for x and y, like there exists x and y, such that this equation is true. Okay, so let's start with the proof of this. Um, let there be a set called S, which equals, you know, S. The components of the set S are these small letter S, which belongs to the natural numbers, and S is any M A plus N B with M and N belonging to the set of integers. Okay, I hope that made sense. Okay, now we're going to do the first step. And the first step is basically just to cover all grounds. But let me just do it. If there are basically four conditions, if a greater than 0, therefore a equals 1 times a plus 0b, obviously. If a is less than 0, so a is negative. So positive version of its version of a equals negative 1 times a plus 0 times b, right? Because negative times negative, because a is negative, equals positive. Same thing with b. If it's greater than 0, then b, absolute version of b, value of b equals 0 times a plus 1b. And if b is less than 0, or it's negative, then absolute value of b equals 0 times a plus negative 1 times b. And the reason we do this, all of this, as you can see, it's kind of in the form of this, m times a plus n times b for all of these. So basically, we kind of proved that S is not a null set because I'm just going to do this because we did assume that they're not both 0, a and b. Both is an a and b. Okay, that was step 1. I'm going to just turn the page for step 2. I'm probably going to give every step its own page. All right, perfect. Now step 2. Let's say there's a number d, which is the minimum, the lower, like the smallest number of S. And now there's a principle called the well ordering principle, which basically just means that for any set, for any non-empty set, there has to be a smallest element, and that kind of makes sense, right? But there's a whole principle made for that. But yeah, so if D is the smallest element of S, then D belongs to S. Yeah, right. That makes sense. And since D belongs to S, D follows the format of that MA plus NB, right? So let's say, therefore, there exist U and V, which are integers. So U and V are actually just M and N, but we just gave it new, new variables, such that D equals AU plus BV. Okay, that also kind of makes sense. Step 3. I got a lot of space. I'm not going to leave another page. Step 3. D divides X for every X belonging to the set S. Now this, I call it like a subproof. So I'm going to prove step 3, which is, going to help me prove the whole lemma. So the proof for that, we're going to prove by contradiction. Okay, so by contradiction, D does not divide X, but X is still a part of S. But we know D is the smallest element of X, so D has to be less than X. That makes sense, right? Because of the well ordering principle, D is the smallest, X is still in the set S, so X has to be greater than D. Okay, and by division algorithm, so basically this is a fancy word for, there exists Q and R belong to Z, such Z is integers, such that X equals QR plus, QD plus R. So this is just, fancy for there's a quotient remainder, because we know they don't divide, D does not, divide easily into X in whole numbers. So yeah, there has to be a quotient, there has to be a remainder. That kind of makes sense, right? So X equals QD plus R equals X minus QD. Right, and I'm gonna name this equation I'm gonna name it 1. We know X belongs to S. Therefore, X equals MA plus NB. Yeah, that's the condition of belonging to X, belonging to S. X has to follow the format MA plus NB. So I'm going to call this equation 2. On the next page, so mixing 1 and 2 together, we get R equals MA plus NB minus QD. Right? That kind of just mix the two equations together. And we also have D equals AU plus BV, right, from the second step. Therefore, we put all these three together. So R equals MA plus NB minus Q AU plus BV. So if you do the whole, if you open it up and all that, we get R equals M minus QU times A plus N minus QV times B. Now M, Q, U, they're all integers. This all belongs to the integer set. This also all belongs to the integer set. So this actually follows the criteria to be in set S, which is an integer times A plus integers times B. So R belongs to S, right? That kind of makes sense. Therefore, R belongs to S. But R has to be less than D because R is the remainder. You can't have a remainder greater than the denominator, or D basically, since D does not divide X. But D is the minimum, is min of S, so the minimum element of S. So all of this doesn't make sense. So R belongs to S. It's supposed to be less than D, but D is supposed to be the minimum element of S. So all this doesn't make sense. Therefore, my contradiction was false. Therefore, D divides X for every X belonging to S. Therefore, step 3 proven. So all of this was just to prove step 3. But yeah, that kind of helps us in, you guessed it, step 4. So yeah, so now this is the last thing we have to prove, which is to prove D is a common divisor of A and B. So we know A belongs to S from step 1, and we know absolute value of B belongs to S from step 1 again. Excuse me. D divides absolute value of A. D divides absolute value of B. Oopsies. Since they belong to the set S and D is the minimum element, yeah. This is all by step 3 actually. So therefore, D divides A and D divides B. Right? I hope it made sense until now. Thus, D is less than or equal to the GCD of A and B. And this is by definition. If, D divides A and D divides B, then D is either the GCD itself or less than the GCD. So I'm going to call this equation A. And now, another thing we know, GCD of A and B divides A, and GCD of A and B, A and B divides B. This is by definition, that's what a GCD is, greatest common divisor. Therefore, the GCD of A and B, has to divide any linear combination of A and B. But we know this equals D. So GCD of A and B divides D. Therefore, the GCD, by definition, GCD of A and B has to be less than equal to D. So I'm going to call this statement B, or equation B. And look at these two. So D is less than equal to GCD of A and B, and GCD of A and B is less than equal to D. This could only mean that D equals the GCD of A and B, right? That makes sense. Therefore, this is all we have to prove, actually. So D is the GCD of A and B, and this kind of proves Bezout's lemma. Again, my apologies if my pronunciation is wrong. But if you do have any questions, feel free to leave them in the comment section below. Like and subscribe for more content like this. This helps, I guess, in the long run if you're interested in math. But this is quite difficult, but this kind of helps in the long run. As you get deeper into math, you don't need to prove all of this, but to know the Bezout lemma, it's quite important. Okay, I will talk to you next time. Until then, peace out.